At a black hole's edge, time slows to a near stop, space stretches infinitely, and no signal, light included, can ever escape. This boundary is not theoretical science fiction, it is a mathematically defined limit of the universe itself, where the laws of physics we rely on simply stop giving answers. The event horizon is one of the most extreme and misunderstood concepts in modern physics. It marks the outer boundary of a black hole, a point of no return where gravity becomes so intense that escape is fundamentally impossible. Once anything crosses this boundary, matter, energy, or information, it is permanently cut off from the rest of the universe. No observation, no message, no warning can travel back out. To understand why the event horizon is so important, you must first understand what a black hole actually is. A black hole forms when a massive star collapses under its own gravity. If the remaining core is dense enough, gravity overwhelms all known forces. The result is a region of spacetime where curvature becomes extreme. The event horizon is not the center of the black hole, it is the surface that surrounds it. What makes the event horizon unique is that nothing physically special happens at that boundary, at least not locally. An astronaut falling toward a supermassive black hole would not feel a sudden shock or wall upon crossing it. There is no solid surface, no explosion, no flash of light. Instead, the change is global and absolute. Once crossed, the future paths of all particles inevitably lead inward. From that moment on, every possible direction points toward the singularity. From the perspective of a distant observer, the story looks very different. As an object approaches the event horizon, its motion appears to slow down. Light emitted from it becomes increasingly redshifted, stretched to longer and longer wavelengths. Eventually, the object seems to freeze in place and fade away. This is not because it stops moving, but because time itself behaves differently near extreme gravity. The event horizon marks the limit beyond which outside observers can no longer receive information. This leads to one of the deepest problems in theoretical physics, the breakdown between general relativity and quantum mechanics. General relativity describes gravity and spacetime with extraordinary accuracy, predicting event horizons with precision. Quantum mechanics, on the other hand, governs particles, energy, and information at the smallest scales. At the event horizon, these two frameworks clash. According to quantum theory, information can never be destroyed. But black holes seem to erase information forever once it crosses the event horizon. This contradiction is known as the black hole information paradox, and it remains unresolved. Some theories suggest information is encoded on the surface of the event horizon itself, while others propose it escapes slowly through quantum radiation. That radiation, called Hawking radiation, adds another layer of complexity. Quantum effects near the event horizon allow black holes to emit energy over extremely long timescales. This means black holes are not entirely black, and not entirely eternal. Yet how this radiation carries information without violating physics is still unknown. Importantly, the phrase, "where physics breaks down," does not mean science stops working entirely at the event horizon. The equations still function, but they stop agreeing with each other. Our models describe parts of reality accurately, but not the whole picture at once. The event horizon exposes the limits of human understanding and highlights the need for a unified theory of quantum gravity. In recent years, direct images of black holes have confirmed the existence of event horizons. Indirectly, the glowing ring of light captured around black holes comes from superheated matter orbiting just outside this invisible boundary. What lies beyond remains permanently hidden, not because of technological limits, but because the universe itself enforces that secrecy. The event horizon is not merely an astronomical feature. It is a fundamental concept that reshapes how we think about causality, time, and the nature of reality. It challenges the assumption that the universe is fully observable and reminds us that some truths may be mathematically real but physically unreachable. If the universe contains boundaries where reality itself becomes unknowable, what else might exist just beyond our current understanding? Subscribe, explore deeper, and keep questioning, because the edge of knowledge is where discovery truly begins.